All right, picture this. You've just strapped on a state-of-the-art AR headset. You pull up a standard, flat 2D photo from your camera roll, and suddenly you step right inside it. It feels like pure magic. But the second you move your head to look around the corner, the entire illusion just shatters. The walls tear apart like wet paper, structures completely dissolve into floating dots, and the scene just collapses. It is incredibly frustrating for developers working on spatial computing. But what if one algorithm could finally hold that 3D world together?
Welcome to today's Explainer. Today, we're diving into a groundbreaking new paper that promises to solve the glaring visual glitches in single-image 3D generation. The system is called InfiniSplat, and it completely reimagines how artificial intelligence translates a flat photograph into a fully explorable, mathematically sound 3D environment.
Here's our roadmap for today. We'll start with the single image problem, compare pixels to surfaces, build a geometric scaffold, decode 3D attributes, check out the state-of-the-art results, and wrap up with the future of view synthesis. Let's get right into it.
Part 1. The single image problem.
So, we're facing a massive gap between our spatial computing dreams and the current technical reality. The ultimate dream, right? You feed an algorithm just one photograph and instantly get a seamless, immersive 3D world for VR and AR. Now, to be fair, current single-image feed-forward methods actually look pretty great, provided you are looking from the exact angle the original photo was taken. But that is not true 3D. The reality hits hard when you move the digital camera farther away or take a step to the side. Under those large viewpoint shifts, current models break down disastrously. You get what researchers call tearing, surface breaks, and loose structures. Digital walls develop massive holes, and objects just completely lose their structural integrity.
Section 2. Pixels versus surfaces.
Before we unpack InfiniSplat's genius solution, let's quickly make sure we understand the canvas we're painting on. We're talking about 3D Gaussian Splatting, or 3DGS. Think of it like generating a 3D scene using millions of tiny, mathematically defined paint splatters, known as primitives. Every single primitive stores very specific data: its exact position in space, how big it is, its rotation, its color, and how transparent it is. Layer millions of these together, and you've got yourself a highly detailed, real-time renderable 3D scene.
Okay, let's dive into this comparison, because this is where the paradigm shift happens. Older methods rely on a pixel-aligned representation. That means they generate all those millions of paint splatters strictly based on the rigid, flat 2D grid of pixels from the original photo. So when you move the camera, those grid-bound points just stretch and rip apart. It's awful, but InfiniSplat introduces a surface-aligned representation. Instead of being chained to a flat pixel grid, it analyzes the depth of the image and aligns the splatters to the actual physical surfaces in the scene, like the slant of a roof or the curve of a couch. Total game changer.
Moving on to Section 3, building the geometric scaffold.
So how does InfiniSplat actually pull this off? It breaks this monumental task down into 3 surprisingly digestible tracks. Step 1 is pre-processing. This is where the system looks at the image to predict depth and extract key visual features. Step 2 is sampling. Here, it uses that depth data to build a 3D geometric scaffold, which you can think of as a structural wireframe of reality. And finally, Step 3 is decoding, where it actually paints those 3D Gaussian splats right onto the scaffold. What's really fascinating here is how that scaffold is built. You start with a perfectly flat input image of a room. But instead of just pushing a rigid 2D grid of dots backward, InfiniSplat uses a depth model to estimate the true 3D surface areas. Then, it distributes its sample points based on those real-world surfaces. It actively places more points on large planes, slanted walls, and tricky complex boundaries. It is literally building a custom 3D scaffolding for the room.
Section 4. Decoding 3D attributes. Now we have to texture and paint the geometric scaffold we just built. To do this perfectly, InfiniSplat uses a very clever dual-branch encoder that splits the job right down the middle. First, you have the Deno branch. This provides high-level semantic understanding. It tells the system, hey, this chunk of pixels is a couch, so make sure it stays consistent as one solid object. Then you have the CNN branch, a convolutional neural network, which acts like a magnifying glass. It grabs all the low-level local texture cues, like the specific fabric grain of that couch or the sharp edge of a table. Finally, a feature fusion module steps in to adaptively balance these two streams, perfectly blending the what is this object context with the what does it exactly look like details.
And here is how everything seamlessly comes together. The core of this system is incredibly tightly coupled. We've got our geometric scaffold on one side and our fused Dino and CNN texture features on the other. The system uses an implicit decoder that acts as the ultimate bridge. For every single point on our 3D scaffold, this decoder queries the texture features and predicts the absolute final updates for our Gaussian splats. It decides exactly where the splat needs to sit, how it should rotate to match the surface, its exact color, and its opacity. It's painting a flawless 3D world directly over the physical framework.
Section 5. State-of-the-art results.
All right, let's talk numbers, because the proof is in the data. InfiniSplat achieved a massive average boost of plus 1.919 PSNR, that's peak signal-to-noise ratio, over the leading alternative method, Sharp, when tested across 4 different real-scene datasets. Let me tell you, in the world of image generation metrics, a jump of this size is absolutely wild. It mathematically proves that abandoning the old pixel grid for a surface-aligned approach is vastly superior. The image reconstruction fidelity isn't just a little better, it's undeniably stronger.
And this brilliantly illustrates exactly what those metrics mean for you and me. When you look at previous state-of-the-art methods and shift the camera angle dramatically, their pixel-aligned primitives just scatter. You end up with these massive jarring holes in brick walls, completely corrupting the geometry of the building. But InfiniSplat holds perfectly firm. Because those splats are anchored to a geometric scaffold that actually understands the surface of the wall, the structure remains solid, coherent, and highly realistic, even from extreme side angles. Literally no more holes in your digital walls.
I think the core scientific triumph of this paper is captured perfectly in this quote directly from the researchers. They state that InfiniSplat reduces the scattered primitives that happen when you force a 3D world to conform to a 2D grid. Basically, they hit the nail on the head. By following the true surfaces of a scene, you generate a robust, structurally sound digital environment.
Section 6. The future of view synthesis.
So why does all this matter? Well, historically, to get a good 3D scan of a room, you had to walk around taking 50 different photos from every possible angle, which is a massive headache and makes you look a bit ridiculous. InfiniSplat entirely eliminates that. It works in a single feed-forward pass. You give it one picture, it does its math once, and bam, you have your 3D room, with no hours-long optimization process. This unlocks true interactive spatial photo browsing on your phone. Plus, it means when you wear an AR or VR headset, your natural head movements will finally be supported by a solid, unbreakable environment generated instantly from just one source image.
I want to leave you with this thought. Think about your phone's camera roll right now. You probably have thousands of standard, flat photographs sitting there. If a single flat image can now instantly generate a coherent, surface-accurate 3D world, what happens when your entire digital history becomes spatially explorable? We are looking at a future where our standard photo galleries are no longer just flat images we passively swipe through, but infinite 3D rooms we can actually step back inside of. Thanks for joining me on this explainer, and keep an eye on how these amazing algorithmic breakthroughs continue to reshape our digital reality.